Hello everyone. We're talking about the stereoisomers in this video. Stereoisomers are isomers. Isomers matlab two or more compounds which will have same molecular formula, but the structures will be different. Now in SL we learned structural isomers. Structural isomers matlab example propane 1 or propane 2 or let's say 1 bromopropane 2 bromopropane. So here, the difference between these two isomers is that the position of bromine only is on a different carbon in this. Like, if I have to interconvert this into this, I have to detach this bromine from here and attach it here. Then I will get this. That means the position of atoms or group of atoms is different. Like something, some atom or some group of atom is on a different position. Or it can be done by branching. Okay, branching is another way to have this structural isomers. In stereoisomers में there is no different position in the bonding or no branching, nothing. In isomers, all the atoms in both the isomers, all the atoms are bonded to the same set of atoms. All the atoms are bonded to the same set of atoms. Then how is it different? It's different because its orientation in the space is different. Okay, its orientation in space or spatial arrangement is different. The spatial arrangement is different. So, considering this, there are two types of stereoisomers found. One is the cis-trans isomers, and the other ones are optical isomers. So, first we'll see the cis-trans isomers. Cis-trans isomers are can be in alkenes or can be in cycloalkane, matlab alkanes which are cyclic, have a cyclic ring. Okay. So let's talk about the cis-trans isomerism in alkenes. So any alkene which has a double bond in it, and more importantly, that both the carbon atoms in the double bond will have two more bonds. Like this carbon atom, apart from this double bond, will have two more bonds here and here. This carbon atom, apart from this double bond, will have two more atoms here and here. So for a stereoisomer, for a cis-trans isomer, it is important that both the carbons will have both its bonded to two different atoms or group of atoms. Two different atoms or group of atoms. So if this is X, this is Y. Okay. Both can't be X. Both can't be X. Second condition is that between the two carbons, there will be one atom or group of atom common. So suppose this also has X. Like this carbon has bonded to X, this also bonded to X. The other one may be Y, or maybe a different element like Z, or a group of compounds or atom or group of compounds called Z. So at least one thing should be common in both the carbon atoms, and both the carbon atoms should have both of its bonded to two different atoms or group of atoms. Like this is X, this is Y, this is X, and this is Z. Okay, these are the conditions in which an alkene will exhibit a cis-trans isomers. Okay, now what is this cis-trans isomer and why does the isomerism exist? We'll see that. If for an example here, cis-butene, butene, butene. You can see that this has four carbons as the name suggests 1, 2, 3, and 4. So 4 carbon atom matlab but. At between carbon number 2 and 3, there is a double bond. So 2 in. Same thing here 1, 2, 3, and 4. Okay. And so but, double bond at carbon number 2 between here. Only difference is that the CH3s here are on the same side. with respect to the carbon bond, this plane. And CH3 is here are on different sides with respect to this carbon-carbon bond. So when the common atom or group of atom is on the same side of the double bond, we call the isomer as cis isomer. The name remains bute 2 in, bute 2 in. That's the same thing. Because I said that the structure wise it's not a different. Okay, the position wise it's not a different. So it will be bute, both have four carbons, both have double bond on carbon number 2. So this name will be common to both of the isomers. But we need to differentiate in the name. So we put the prefix of cis for that isomer which has both the common ones on the same side, and trans for the isomer which has common atom or group of atom on the opposite side. So that's how the isomerism, cis-trans isomerism will exist. Here, cis 2 bromo bute 2 heme may, the common one is again CH3, CH3, even though this is different, this is HBr, that doesn't matter. You pick up the common one. So common one, common atom or group of atom are on the same side, common atom group of atom on the opposite side. So this will be trans isomer, this will be cis isomer. So alkenes will have cis and trans isomer provided none of the carbon atoms should have both the bonds bonded to the same atom or group of atoms. For example, if there is, suppose there is H and H, both are same. Okay. And this is H and bromine. This will not give rise to cis and trans. The reason is that even if I take the other way around, like if I rotate this here, it will be the same isomer. Because either H same side mein hai, if I rotate this, HS will be on the same side. So it will not give a different isomerism. Even if this H comes here, it will be same with this. Same side pe here. So it will not give rise to a different structure. Okay, so it's not a cis-trans isomer if any one of the carbon atom has both the atoms or group of atoms bonded to the carbon atom are same. So that's about cis and trans isomer in alkenes. Now cis and trans isomer can also be in cyclic alkanes. Cyclic alkanes matlab, like this is propane, 3 carbons. Ane matlab single bond, but in cyclic form. So the 3 carbons are making a cycle. In this case, if there are 2 chlorines bonded to them, one on carbon number 1, one on carbon number 2, like these two, then if these two are on the same side, then cis isomer. If these 2 chlorines are on the opposite side, then trans isomer. Okay. The cyclic compounds also will have cis and trans isomer, depending on if the common atoms and group of atoms are on the same side or on the opposite side. Okay, so that's all about the cis-trans isomers. Now next is optical isomer. Now optical isomer is a special type of isomerism which is seen in only those organic compounds which have at least one carbon atom. Carbon atom should have 4 bonds. And this is the 3D structure that we write. These two are in the same plane of the paper. This is coming towards you and this bond is going away from you. So these 2 bonds are in the plane of the paper. The wedge is coming out of the screen towards you and this dotted line is going out of the screen, behind the screen, away from you. So this optical isomerism is seen in only those compounds which has any carbon, even if one carbon, which has all of its bonds bonded to 4 different atoms or group of atoms. 4 different atoms or group of atoms. For example, this is W, this is X, this is Y, this is Z. All 4 atoms and group of atoms should be different. Only then that compound will exhibit optical isomerism, and there will be 2 isomers of this. There will be 2 isomers of this. Example you can see here, like this carbon atom is bonded to CH3, C2H5, H and OH. So this will exhibit optical isomerism. That carbon which has all the 4 bonds different is called as chiral carbon. So in some compounds, you can have more than one chiral carbon also. But at each chiral carbon, there will be two isomers. Now, these two isomers are mirror images of each other. For example, this one and this one. Now, at a glance, they look same, but they are not same. They are different. Okay? They are different. We'll see how exactly they are different. So, you can see that these two molecules which are having that chiral carbon, you can see that the four different atoms and group of atoms that are shown here are by different colored balls there. So red, purple, yellow, and white. Okay. So these two molecules look same, but they are mirror images. So two things you need to understand here that they are mirror images. So if there is a mirror here, then if this is an object, this is a image. Okay, so they are exact mirror image. No, red to red, yellow to yellow, purple to purple, etc. So this is a mirror image. But how do you know that they are not same? If you look at this picture, if we keep one on the other, like try to superimpose, then red and red is getting superimposed, purple and purple is getting superimposed, black and black is getting superimposed. But you can see that yellow and white, they are not. Which means that these two molecules are not identical, they are different. Okay, they are not identical, they are different. So that's how we know that the two molecules are different, they are not the same. So those are the optical isomers, and they are also called as enantiomers. So enantiomer and optical isomers are same. Basically, enantiomer matlab two non-superimposable form, like the two ones which I've shown in the picture before, and these two which are shown here. Okay, so CH3, CH3, CC and C2H5, they are getting superimposed, but H and OH are not getting superimposed. So those are enantiomers, which are optical isomers. Now something on polarimeter. If there is a carbon atom, which is a chiral carbon, then it will have two isomers. How do these two isomers behave differently? One of the property that they show different is that they can rotate the plane of the polarized light. Now, what exactly is this? This is the experiment of the polarimeter. A white light from a light source. A light is basically a dual nature. It's a particle and as well as wave. So we consider the wave nature in this. So if it has waves, then it will have oscillations. Now oscillations can be in any planes. So there are infinite planes which are shown by here. You can see that these are the planes of the oscillations. So there are infinite possible planes in which the waves will oscillate. This is unpolarized light, like the normal light is unpolarized light. If you pass the light through a polarizer, it will cancel out all the other planes and keep only one plane. So then the wave will only oscillate in one plane. This is a polarized light. Now this is a polarized light. Polarized light will have only one plane in which the waves will oscillate. If that light is passed through a container which contains an enantiomer, which means one of the optical isomer, then as it passes through this, as it covers the journey through the container, the plane of the polarized light will rotate. So you can see that this is the plane, this is the plane. From here to here, it has rotated. From here to it has rotated more. From here to it has rotated more. So when it entered, it was this plane. When it came out, it is this plane. So entered, it was this plane. When it came out, it was this plane, which means there is a rotation of the plane of the polarized light. This is the feature of an enantiomer. But I said there are two optical isomers, the object and the mirror image, the two mirror images. If one of the isomer is rotating this plane, let's say by, this is clockwise, let's say 27 degree, then even the other isomer will rotate by 27 degree only, but anti-clockwise. Oh, not centigrade, just 27 degree. So this means that both the optical isomers can rotate the plane of the polarized light, but in opposite direction. One will rotate it clockwise, the other will rotate it anti-clockwise. So if I take a mixture of both, like 50-50% of both the isomers, then both isomers will rotate the plane in opposite direction. So as an effect, as a result, the light will come out and the plane will be unrotated. So there will be no rotation in the plane of the polarized light if there is a mixture of the two isomers, optical isomers, half, 50% and 50%. Now this is called as racemic mixture. So you can see 50%, 50% mixture of the two isomers is called as a racemic mixture or a racemate, which does not rotate the plane of the polarized light. Hence, the racemic mixture is optically inactive. Optically active matlab it should rotate the plane of the polarized light, but this does not. So individually, each of the isomer is optically active, but the mixture of both of them, 50%, 50%, is optically inactive. Okay, so that's all you need to know about the stereoisomers, both cis-trans isomers and the optical isomers.